So thank you everybody for coming today. Talk tell us about relative Calabi-Yau structures for Legendrian Contact Homology.
So first, thanks everyone for both for the invitation and for coming. So I just say this is joint work with Jason Ma, who is currently a student of Lenny's down at Duke, but was my undergrad beforehand. And also the very last part, depending on how far I get, we'll see, is also sort of in conversation with Zhenyi Chen, who is a student of Eric Zasloff's at Northwestern right now. Okay, so my goal for today is to tell you a story about a development of ever more sophisticated analogues of Poincare duality. So again, a story of ever more sophisticated analogues of Poincare duality for Legendrian Contact Homology. Hopefully explaining the title by the end, but not necessarily getting all the way there. I know there's some more contacting people here. There's more symplectic people here. So let me quickly motivate a little bit more for the latter. So like Lagrangian submanifolds in symplectic topology, Legendrian submanifolds play a central role in the study of contact topology. They are, for example, as Bulin well knows, the locus of for contact surgery constructions. They're the boundary of nice Lagrangians and symplectic manifolds. And on one hand, they have some lovely classical, very topological invariants, or the Thurston-Banach number, which sort of says how much the contact structure spins around the Legendrian, and the rotation number, which is how much the Legendrian spins around in the contact structure. So those play a central role, but the study was revolutionized about 25 years ago. I'm looking at Helmut, about 25 years ago. I can't count.
Well, yeah, so in 2000.
Around 2000.
So we had some ideas beforehand, but then there was this publication of Vision 2000. Mm-hmm. And then we decided to write it up ultimately.
Yep. So around 2000, around 25 years ago, there was sort of a development of non-classical invariants of Legendrian knots. The first using holomorphic curves and generating families. And then later on became constructions from Hegardt-Fleur, and most recently from sheaves. And understanding the structure of such non-classical invariants can reveal sort of more geometric insight. It can deepen connections, for example, to Fukaya categories to those sheaf invariants. And that sounds like very highfalutin, but really the motivation. Oh, this is being recorded. Maybe I shouldn't say this. But anyway, the motivation is that I've been looking at this stuff in 2000 corresponded when I was a young grad student. And I've been looking at this stuff for a long time, and you start to notice patterns and you can't stop thinking about those patterns. And so this is, in a sense, this is a very selfish project. I love this stuff. It's fun. There's some interesting patterns. I want to explore them and see where they go. In case anyone from a journal or something looks, I didn't say that. There's deep, important connections to other parts of mathematics in what I'm about to do. All right, so let me just make a quick note. So in order to cover sufficient ground, I can take liberties with some definitions and will certainly not be as general as possible. But hopefully I'll tell you when I'm lying to you. That's my promise. Okay, so let's start off just with just to get things back into our heads. Let's start off with a review of Poincare duality. There's a C in there, isn't there? Okay. And again, the goal is just to make later analogies more clear, because I'm just going to be drawing the same diagram again and again and again and again, just with different terms in that diagram. So this is just really just duality for a manifold with boundaries. So we'll have a nice manifold with boundary, and I'm going to think of the following diagrams are really coming from the Morse homology of F that's sort of nice near the boundary of L. In particular, it's going to be tangent near the boundary of L, and everything's going to be going towards the boundary of L. No flow line comes out of the boundary. And in that case, you can think of, well, there's some lovely long exact sequence of the L. I meant L the entire time. And there's some lovely long exact sequence of the pair. On the top, and then on the bottom, you get the long exact sequence of the pair in homology, and then the related and all the vertical maps are the Poincare duality isomorphisms. So. And then these are all isomorphisms, where this is the usual Poincare duality. This is some kind of relative Poincare duality, but all of these are sort of capping with the fundamental class of the fundamental class of the manifolds. Okay, and I want to think about this slash that, whichever, as a cone. As a cone on the connecting homomorphism between the relative homology and the boundary. And a nice way to see this is you can sort of think of the boundaries in that Morse theory picture that I gave you earlier. You can think of the boundary as a subcomplex. And then the connection homomorphism is just the maps that come from the interior, from critical points on the interior out to the critical points on the boundary. Right? And again, so you can think of those maps as giving connecting homomorphism of the long exact sequence of the pair. Okay, so hopefully this is nice and familiar, like if I do. So unlike the talk that I'll just say, and we'll just use this as motivation. Okay. All right. So let me remind you / tell you / pseudo define Legendrian contact homology for a knot in R3. With the good old standard contact structure, because that's already complicated enough. And what we want to think about is this Legendrian contact homology is some kind of combinatorial realization of doing Morse theory for the action functional on the path space of the Legendrian. And the upshot of this analogy, let's just think analogy for now, not trying to be too precise about it. The upshot of this analogy is that the Legendrian contact homology so it's going to take the form of a free unidal tensor algebra, a free differential graded unidal tensor algebra. And that's a straight up capital A for those of you used to this theory. So we're going to take some vector space, we're going to take its unidal tensor algebra, and then we're going to define a differential on it. And all of the geometry is going to be sitting in the differential, not in the algebra itself. Okay. And let me tell you what these things are. So I'm going to let A be just the vector space generated by the Rabe chords of the Legendrian / in this lovely well-placed picture, the crossings of the projection to the, of the projection to the xy plane. Okay. I should be working over Q adjoined the first homology of the Legendrian, but I'm just going to pretend to see mod 2 for today. Okay. Yeah. Right, and then the differential, I'm just going to determine this on generators using certain immersed curves in the xy projection. Those immersed curves are secretly holomorphic. And let me, instead of defining them in complete abstraction, let me just define them by example. Okay. And by the way, so these immersed curves are going to have. So well, let's look at this diagram for a moment. You'll see that at every crossing, I decorated every crossing, the quadrants around the crossing with positive and negative corners. Secretly, the positive corners are going to positive infinity and splictization. The negative corners are going down to negative infinity, but just nice and combinatorial. And I want to look at immersed curves that have one positive corner and possibly multiple negative corners. So one positive corner and maybe multiple negative. So for example, if I want to take the differential of T1, and is that too low? We're good? Is this, okay. So we're going to take the differential of this crossing. Well, there's a lovely disk right here with one positive corner and some other negative corners, which will give us a differential of 1. There's another one over on this side, which has these 3 corners. And I'd write that counterclockwise order as A1, B, C. And then there's one more, which would be sort of doing the same thing, take a turn at A1, have a corner at A1, but then sort of pass through B and C. And that would be the differential of T1. Okay, are we good? Vaguely familiar? Helmet, bringing back memories is the thing you're supposed to be yelling at me about. Yeah. Okay, let me also say this is, I'm not going to say much about the grading. It's some kind of Calabi-Yau index of the rate chords. But let me just tell you that the grading would have that all of the TIs would have grading 1, all of the AIs happen to have grading 0. Grading of B is right. One of them is 2, one of them is -2. Oh, B is -2. And C happens to be 2. This is just for future information. I did not tell you how to do that. Okay. All right, and then the theorem. And we'll attribute this both to Shikhanov-Ashberg. It's a comma, not a dash. Again, around late 90s, 2000s, somewhere in there. Is that, well, this is a differential graded algebra, right? So d squared is 0, and the homology is invariant. With homology. Invariant of the Legendrian. Okay. All right. So it turns out, so we have an invariant, and no no mere mortal can compute this thing. In other words, Lenny can compute it, but no one else can. Right? So no mere mortal can compute this. So how do we compute it? That's not fair to Steve Sivak, actually. I think Steve Sivak can also compute this.
What does compute, so meaning like describe all the differentials of the.
Well, describe the differentials, no, a computer can do that. The question is, can I hand you two nuts? You compute the DGAs for both of them, and then can you use those DGAs to actually tell them apart?
Yeah.
That's sure. Yeah. No, but like actually computing the differentials, like there are multiple people who've written computer programs to do
Yeah,
this.
that's like an exercise. That's just an exercise, right? I mean, that's something you could give to a.
It's undergraduately computable.
Yes.
And I have the papers to prove that it's undergradually computable. Okay, so how do we compute this thing? Well, so if you don't understand the algebra, well, there's two perspectives on this. One perspective is if you don't understand a nonlinear algebra, well, you can look at its representations. Right? So we'll call these things augmentations. We'll call them epsilon from our DGA to sort of the trivial DGA, which is just the ground ring with the zero differential, also sort of concentrated in degrees here.
What is F actually? Yeah.
Well, okay, for today it's C mod 2.
So that's, I guess, the problem, because if you had F equals Q, then there's like things like solid and minimal algebras, like there's like various invariants of DGAs, which are kind of homotopical.
But we can make it over Q. I just didn't want to tell you how to do. I just didn't want to tell you how to do the signs.
Yeah. But then can one use things like minimal algebras, like solid and minimal algebras, to differentiate?
The answer is maybe. Can you ask your question again in about 5 minutes?
Sure.
Because I think what I think of as minimal algebras and in my head I sort of like minimal models for A infinity.
Yeah,
algebras.
minimal models. Yeah.
Yeah, but the answer is yes, but to get to them you kind of need to do this because this isn't as somehow this DGA. Let me answer your question in 5 minutes.
Sure.
It's a great question, and I promise. I promise I'll get closer. Okay. All right, so we're gonna look at representations, and we're gonna call these augmentations. Right, so you either think about these as representations, which sort of gives you one sort of way to generalize them. You can think about higher dimensional representations, which I'm not going to talk about. Another way you can think about this as that these are actually, well, you can think about setting the differential, which is just a bunch of algebraic equations, sort of just say, see where the differential is 0, that gives you an algebraic variety. And then the augmentations are just the solutions, like just the points in the algebraic variety. That's another way to think about it. All right. And then you can use these augmentations to linearize linearize the algebra. This is my idea of Jaconos. And I'm not going to tell you exactly how to do this, but a good way to think about it, is the following. Is you can think of an augmentation as just a way of decorating a certain choice of generators, a certain choice of crossings. So here's an augment. That plays nicely with the differential, and I promise what I'm about to draw is an augmentation. And my initial numbering had absolutely nothing to do with this. No, everything. It had everything to do with it. Okay. And what you end up counting for this augmented differential so it counts disks again, but now it counts disks where all but one of the negative corners is augmented. So you just sort of ignore all of the augmented corners. Okay. But this is leading to your question, as is actually just the first step in defining an A infinity algebra, and even better, an A infinity category. So this is the first step. In defining what we now call augmentation categories. Say plus minus of our Legendrian, and these were first done by Bourgeois and Chantrain. In 2014, and then sort of refined. Well, aug minus was defined by Bourgeois and Chantrain in 2014. They did not call it that, and then refined by Lenny Ng, Dan Rutherford, Vivek Shende, Steve Sivek, and Eric Zaslow in 20 to the form that I'm going to tell you about to the form I'm going to tell you about in a second. Okay. Now, so there are categories. I need to tell you the objects. I need to tell you the morphisms, and then there are A infinity categories. I also need to tell you the structure maps. Okay. So the objects, well, are augmentations. The morphisms, well, as is sort of usual with the Fukai category type setup, the morphisms are really, really boring, and all the information's in the structure maps. Just like before, the algebra here was kind of boring, but there's good information in the structure maps. So in this case, we'll call, say, Hom minus of two augmentations. I'll just let that be, well, just my good old, just the original vector space that I was talking about, except for what I really want to think about it is the vector space, dualize it, and then shift it. And then shift the gradient. This is just to make the structure maps have the right degrees later on. Right? And then so that's Hom minus, and Hom plus is slightly more complicated. So we'll take Hom minus, and then we're going to add on sort of the some kind of Morse complex for a perturbing function in the neighborhood of Legendrian. And really, from a very practical standpoint, we can think about that as having one max and one min. That I'm going to label, say, I don't know, somewhere on Legendrian. Okay, now again, I still have to take the structure maps, but from here on out, for simplicity, I'm just going to assume that the augmentations are equal, not because that tells me anything, but because it means I don't have to write down as much.
Sorry, can you say again what's going on with the so you take them minus the gray minus one elements and the homomorphisms minus why?
Oh, like this minus one, you mean?
Yeah.
This is just take take the old grade chords and just, they have a grading, just
Okay.
shift the grading.
Shift the grading.
Just shift the grading.
Great. Well, first, why do you have minus and plus? It's a dumb question probably, but why do you split your homomorphisms to minus and plus? And what is the plus part?
Okay, so thank you for, because I was not clear. These are two different augmentation
Oh,
categories.
Okay,
There's the negative augmentation category has this sorts of morphisms, and the positive augmentation category has this sorts of morphisms.
okay.
Thank you. That's a good,
The positive one's like unitable, so
and the,
it's much nicer than the.
right. So somehow, like the natural one, so the natural one to define, well, not the natural one, the easy one to define is hom minus. And that's what we're trying to define, and secretly what John and I defined, like sort of just, that is what you get just by taking the DGA and just flipping it around. And taking factors. Hom plus is more complicated, because you can't just get it from the original DGA, you actually have to add in a little bit more geometric information into it.
Okay, so what is the definition of the homomorphisms? Plus, I just can't read what you wrote.
Oh, for hom plus, so I'm just gonna take the rate chords.
Huh?
And I'm just gonna add on, I'm gonna take my my Legendrian, I'm just gonna perturb it a little bit by some kind of Morse function f on the Legendrian itself, and I'm just gonna take the Morse complex of that perturbation.
Okay, and in the hom minus there, it's still epsilon prime?
Yeah,
Also, the HOMs are like just the space of generators, right? Not the algebra.
right, yeah, I deliberately did the slick thing about calling this the
Calling
tensor
it
algebra.
TA. I see the tensor. I see.
So this could genuinely just be
Yeah, never
vector
mind.
space.
Okay.
This is just the vector space.
Okay.
Well,
That's a trap.
okay, I guess you're gonna say what the compositions are.
Yeah, I will not say what the compositions are. Right, because there's no geometry yet. I'll leave that up. Okay, so what are the, yeah, so. So structure maps, and again, maybe our notation will be there. So they're going to be sort of k-fold structure maps, one for each case. Yeah, maybe I shouldn't define both categories at once. One for each category, or one set for each category. That sort of eat k things in hom plus or hom minus respectively, and spit out something in hom plus and hom minus. And really what these come from, well, what I'm about to say is strictly true for hom minus and almost true for hom plus. They just come from sort of this switching to this augmented differential, and then reading it backwards and just taking acurates. Okay. So for example, let's try to read M1, I think I'm just gonna do minuses for now. M1 minus of A3 in this example right here. So what M1 minus of A3 would be things that have one negative corner at A3, possibly other augmented negative corners, and then one positive corner. Okay. So in particular, here are one more color.
So there's some kind of algebraic duality, like some kind of Cauchy duality.
It's a Kobar construction. They're like a.
Yeah, it's the Kobar. Yeah,
Yeah.
I'm slowly doing the Kobar construction. That's right. Like what's the mantra is that the dual of free DGA is a co-free co-algebra. So it's something.
Yeah.
It's something like that. But I didn't understand those words when I first started working on this, so I didn't want to use those words immediately when you give your talk. Okay, so for A3, for instance, this disk right here, so that is from this negative corner to that positive corner, so I'll get a T3. That corner is augmented, so I can ignore it. So I'll get a T3. But I'll also get this one, which is with a T4, because I have a negative corner augmented, and then the positive corner T4. So that's how to compute one. And I'm just doing exactly what you just said. Okay. Here's another example. So let's do M2 minus of BC, right? And M2 minus of BC is actually exactly this blue thing drawn here, right? So I have a disk with, well, now two negative corners, one positive corner, and that augmented corner, which I'm going to ignore. So I've got T1, I hope. There's another one, T2 also, but let's just say, let's just call it T1. Okay. And then, oh yeah, actually it's just T1, because then M2 minus of C comma B, that would be right here, negative corner C, negative corner B, augmented corner, and then positive. And so that's just T2. So the order doesn't matter. Let me not tell you exactly what HOM plus is, but except I do want, let me just note that in HOM plus, sorry, in not HOM plus, but ON plus, we can think of HOM minus, sort of and it's not HOM minus, right? So minus is an A infinity subcategory. And as Julian did before, that minimum Y is sort of acts as a strict unit. Okay. In particular, if we want to look at the linear complexes, if we want to maybe just sort of look at the linear complex or the underlying homology here, we get something like this. Well, let's see, what do we get? So for cohomology of minus, I'm going to get, that turns out that's going to be generated by B, C, and then any one of the T's, they're all, it turns out they're all equal. And notice that since I've shifted, that's going to be degree -1, degree 3, and degree 2. And then for HOM plus, this time I'm going to get B, C, and Y. And this time, so again, I'll get -1, 3, and then Y is our lovely unit in degree 0. Okay. And if you stare at that for a moment, and you pretend that we're looking at, say, Poincare duality for a surface, you say, oh, here's Poincare duality for a surface. -1 is dual to dimension -1 is dual to dimension 3, right? Okay, no one believes me, but that would if it's a surface and you could have negative dimensional things, that's what the duality would be. This looks like the fundamental class of a surface, and this looks like the class of a point. And in fact, that's exactly what's going on. Even better, I'll say this briefly and maybe try to come back to it. Even better, the duality between B and C, you can see from this disk right here with two positive ends. Is how it's telling you that B and C are dual, as if they were sort of part of a surface. I have to say, by the way, that that's real. This really is Poincare duality. If you're Legendrian bound to Lagrangian in this splicization, this is the Poincare duality for the for that Lagrangian. Now, why the dimensions -1 and 3? The particular Lagrangian this one bounds has mass log number 2, and so you have to take the gradient spot. You have to take the gradient spot 2. So -1 and 3 or 1 on 2. So it works out. Okay, so let's talk about duality sort of in the linear case. Let's take this observation and turn it into a theorem. All right. So there is the symmetry that I noted here, and even this positive disk that I noted here are are examples of a more general phenomenon. So here's the theorem. So I proved this back in 2006. It got upgraded with work that I did with Tobias Ekholm and John Etnier in 2009. That's sort of to higher dimensions. The way I'm going to write it was actually just how NRSSZ, that's what I'm just going to refer to these folks. I'm going to write it in the way that they reformulated it in their paper. And then I'm going to go one step further and reformulate it in, dang it. I erased the draw. I'm going to write it exactly in the exact same place where I wrote the Poincare lattice duality. And I'm going to reformulate it in a slightly different way. But at heart, this is from 2006. Okay. All right. So the theorem is that you can think of Hom plus sort of from this thinking about Og minus as an infinity subcategory. You can think of Og plus as the cone on some kind of map from Og minus to the Morse complex, to the Morse complex. And so I'm going to write sort of the top line is going to be the logarithmic sequence of that cone as sort of at just at the linear level. So cohomology of Hom plus to, well, let me just write it as a cohomology of Legendrian to cohomology of Hom minus. Right, I think I'm writing this exactly where they were before, and then that's dual to the homology Hom minus the homology of Legendrian, and then the homology of Hom plus, where the vertical things are this vertical is really, honest to God, Poincare duality, right? Is this just really sort of the Morse complex, or it's sort of like Poincare duality on the Morse complex, and these two are also isomorphisms, with this map right here being the map that sort of comes from this two positive corner thing. So I'll write it like that, and I'll call this eta, and the map going down this way really is some kind of capping with the fundamental class, and I really mean that as sort of capping with this kind of fundamental class here. Okay? And you can actually you can write down explicit versions of these maps, sort of using homomorphic. Right? All right, and then again, as I mentioned before, and I really am mad at myself for erasing the earlier thing, is if you blur your eyes and think about where everything was in the original diagram, it's the same thing. And further, by the Seidel isomorphism, it literally is the Poincare leftist duality for a filling Lagrangian relative to its boundary, relative to the Legendrian boundary. Of course, this also works if you don't have a Lagrangian filling it too. So, but if you do have a Lagrangian filling it, this is just the same thing that I had written down before. Okay, so this is all old news. I could have given this talk in 2006, except for the notation. Are we on the same? We're on the same place. We good? Okay, because now I'm going to add some. Now I'm going to add some newer. Now I'm going to add some newer stuff.
Is there any additional easiness or better properties if there is any Lagrangian filling, like for this formulation?
Oh, from this formulation as opposed to like the old formulation?
As opposed to like a Lagrangian that it doesn't have a Lagrangian filling.
Well, let's pretend for a moment that your Lagrangian had this. You can actually use this as an obstruction to finding an orientable Lagrangian filling, for example. Right. And so you can especially think about it in terms of in terms of degrees, like sort of Maslov degrees. Let's pretend your Lagrangian has. Let's try to ban Maslov zero Lagrangians, for example. Then these degrees had better exactly match the homology of the surface. So, for example, this does not have a Maslov. This can't be the boundary of the Maslov zero Lagrangian because those ain't one. Right. So, yes, is that the question you're getting at? And in particular, you can also, I guess you could also ban any kind of orientable Lagrangian filling independent of Maslov. You just have to have mod 2 the same Maslov degrees of a surface.
And so this one's not Lagrangian.
It is actually because mod 2, those are 1. So mod 2.
Oh, so it's a mod 2 thing.
So for orientable, if you want to ban orientable ones, it's mod 2. So this one is the boundary of a Lagrangian torus, but it's Maslov, so Maslov 2 Lagrangian torus. Okay. So
I see. Yeah, with the Maslov index. Yeah.
the Maslov index.
That makes
You
sense.
have to take the exactly. So for example, the figure 8 that we were talking about before, if you look at that one doesn't have an orientable filling because all of its all of its homologies, all this sort of linearized contact homologies, basically they have they sort of have. I'm a little messed up because I usually want to say odd or even, but I've shifted the degree, so odd and even have just switched. It has the wrong homology. It has the wrong homology to be. It's got a perfect homology to be the boundary of a Klein model, though, which is true. Is the boundary of the Klein model. Okay, so the next step, the next thing we should probably ask ourselves, given that I've set you up this way, the next step to ask ourselves is, well, how do we? So this was all linear information. Although I told you that there's nonlinear information sitting here, how do we start adding back in the nonlinear? How do we start adding back in the nonlinear information? I should also warn you that we are now right at the limit of my algebraic understanding. I've used this. The other benefit of this project is that I've learned a lot of algebra, but only so much. So you can feel free to ask questions, and my response is going to be, "That's a great question. Let me go learn enough algebra to figure out what the hell just went on." If you don't learn anything from a project, why are you doing it? I'm leave that up. Okay, so now we're going to enter the realm of weak relative Calabi-Yau structures. And this really is sort of the new material in the talk. And again, our goal is to try to add back in nonlinear information, in other words, sort of M2, M3, et cetera, into this picture. And the proper framework is that of, well, a weak relative Calabi-Yau structure. So these were first formulated by Kontsevich and Sodelman in 2001 for analogues of closed manifolds, and then generalized to the relative setting by Broff and Dickerhoff in about 2019. And I should say that the hardest part of this entire project was just finding the right framework. Right? Somehow, once you find the right framework, it's not. I mean, there's still difficulties, but finding the right framework just to write this down was actually the hardest part. So this is Kontsevich Sodelman. So they did the original Calabi-Yau structure for infinity structures, and then Dickerhoff in 2019 sort of did the relative version of the relative version of this. I should also mention that Zhenyi Chen, who I mentioned sort of as a sort of a pseudo collaborator before, has a different approach to the idea that I'm about to give you. He's currently writing out. Okay. So the algebraic idea is we're going to think of all of Hom plus and minus and the Morse complex, not as vector spaces, but as A infinity bimodules over aug plus. And what I mean, what I mean by that is that again, the underlying vector space is the same as above, right? And now the structure maps. And sort of the actions of aug plus slash the structure maps of the bimodule, sort of given, well, given by the following. So there's I want to define sort of n, and so M was my old structure map, and N are my bimodule structure maps. They have to take in R inputs on one side, S inputs on the other side, and then something from our vector space in the middle. So we'll have to take something from Hom plus R of those, and then either Hom plus or Hom plus, Hom minus, whatever. We'll just call it. And then S copies of Hom plus on the other side. I've got to get back some kind of thing in Hom plus or minus on the other side. And let me just define it by a picture instead of defining it. I don't know if I need this anymore, but I worked too hard to erase it.
Don't take risks.
Like some responsibility.
Exactly. It's completely a fallacy in this case, but it's so pretty. But let me define it by a picture instead of by anything else. Where if I take some kind of like maybe AR to A1, tensor sum V, tensor sum, say, B1 to BS, and I'm to give me W, what that should look like is I should have a V at a negative corner, the W at the positive corner, so like V to W as we usually do, and then I should have all the AIs up here at negative corners, by the way, and all of the BIs down here, and possibly I'm also might be ignoring some augmented corners along the way. So this from the A's, V, and B's, I get out W. And so that's what that, and so it's still contained in pictures like this. It's still contained in pictures like this. Mostly. Right? And then we can let's call the associated bimodules. M, no, that's supposed to be an M. M plus or minus and N. Okay. And then the theorem, whose proof we're almost done writing down, is the following. So this theorem, this is Jason and me, and then Zhenyi sort of has a slightly different approach, a slightly different technical approach with the same result. And that is that the projection from sort of the Hom plus bimodule to the Morse theoretic to the Morse theoretic bimodule, this carries a weak right relative structure, and basically what I'm going to define it in the middle of never do what I'm about to do, right? I'm going to define this structure in the middle of the theorem. But the way I'm going to define what this is, I'm just going to draw this again and say that's the definition of a weak right relative Calabi-Yau structure. Okay, so I'll just draw that again. Where now I go M plus to N to M minus. There should be a degree shift in here too somewhere, but I think I'm gonna get that wrong, so maybe I won't write it down. And that goes to M minus dual to N dual to M plus dual. And again, there's some gradient shifts that I'm just not going to tell you about. Right? With gradient shifts to make it match the correct gradient shifts here. And with the vertical arrows, all being quadratic isomorphisms. And I can even tell you what this map here is. Unfortunately, it's the wrong map. It's the wrong way. Where that map is exactly things that look like this, where you have maybe multiple bimodule inputs on both sides, and then but now you have sort of that's sort of secretly going from positive corner to positive corner. It's what's giving you the duality. Right? And maybe I should make let me end with 3 remarks about this. I'm not gonna go through the proof. Mostly because it's also like way too late to give you the proof. So let me make 3 remarks. So the first is, so aside from just figuring out what the framework should be, So aside from just finding the framework, the difficulties, those are the main difficulties of the proof are the following. So the first is that the natural like eta that you like the duality map that you see goes the wrong way for the structure you want to prove. Right. So and there's some cute algebraic it's not just algebra. There's some cute algebraic way of reversing it. It's not just taking the adjoint. It's more complicated than that, but there's some kind of cute algebraic reversal, which Jason and I are calling the algebraic gadget. And it's not the same kind of gadget from Oppenheimer that we were just talking about before. And then the second difficulty, no, it's actually because it makes things work instead of the opposite, instead of the exact opposite, right? And then the other difficulty is just finding the right geometric structure to capture all of these maps like in a natural way, as opposed to just BSing your way through. But to really capture these maps, you have to think hard about the geometric structure. That what you end up having to do is you take your Legendrian, you take two copies of it, one copy really far above the other. Then you take R copies of this one and S copies of this one very closely, and you have to order them in exactly the right way, and eventually it works. So I guess that's the first remark. Just like, what are the difficulties? Otherwise, this would seem trivial, right? Why did it take me so damn long? Because it was hard. It was hard for me. The second thing is that this isn't really how Brough and Tikhonov formulate the weak relative Calabi-Yau structure. They formulate it as they would formulate it actually as a class in the Hochschild homology of the underlying infinity bimodule. This is some kind of non-degenerate. In some kind of non-degenerate class in the relative function homology. And somehow, so closed is equivalent to these, everything here being nice A infinity maps, and non-degenerate somehow is that these are all quasi-isomorphisms. That's what, except I can understand this better than I understand this. So I wrote it that way. And then finally, although I introduced this so I could say the final thing, so the next step, and this is what Jason and I are talking with Zhenyi about mostly, is to go from Hochschild homology to cyclic homology. And in fact, this diagram really should lift to some kind of relative cyclic structure. Exactly what that should look like is part of the problem. But if you're interested, although my time's up, so I'm not going to tell you right now. If you're interested, I could give you an example and I could just show you what that cyclic structure is. It's really, I mean, I can just draw the damn thing, and it's kind of easy to see in examples. But let me end there, and thanks for your attention.
What does cyclic homology have to do with this picture? I didn't really.
I don't understand it either. That's a great, yeah. I don't. So you can see what cyclic homology should be if you think about this picture as capturing something in Hochschild homology, and then you can think about lifting. I don't know how to translate cyclic homology into this picture. I know how to translate. Let me do this after all the questions. I can just draw you a picture and show you why this structure should be cyclic, but it's not clear unless Thomas is about to tell us. No.
No. But I mean, cyclic, you would expect that the cycle will record stuff. So
right.
So maybe you want also to think about this thing not in S3, but in some like S1 plus.
Should I just shut up and just draw let me just draw the other example and I'll show you what I mean actually. So This isn't, what I'm about to draw isn't like 100% right, but it's close enough for our purposes. Damn it. I have to draw to the front and then resolve it, because otherwise I can't do it right. Okay, now pretend you didn't see that. Okay, so, and by the way, these are all sort of pluses this way and minuses on the top, and the bottom is just the way I drew it over there. So if we call this, I have to have drawn this beforehand because I knew someone was going to ask this question. Let's call this A1, B1, and C1 here. So A1, B1, and C1 here, and A2, B2, and C2 here. And let me just say, let's start computing, say, cup products, right? So the cup product, I can compute the cup product of A1 and C1. So A1 and C1, that would be sort of two negative corners and one positive corner, I get B1. I do the cup product of C1 and B2, I should get A2. Let's see, so C1 and B2, that would be this disk. So A2 would give me C1 and B2. I get A2, and if I take the cup product of B2 and A1, I damn well better get C2. Let's see. B2, so that's this disk right here. So B2, A1 gives me C2. And if you look carefully, B1 is exactly sort of the dual of B2. A2 is the dual of A1, because I set this up this way, and C2 is the dual of C1. And you sort of see there's a nice cyclic permutation going all the way through. That's what the cyclic action should be capturing. How to see that diagram? But that's what it should capture. The funny thing is, I think I saw this before. I observed this before I thought about any of this other stuff. This is like the first thing. So. Did I not answer your question interestingly?
No, I'm good. I'm good. Yeah.
Well, no, I know I didn't answer your question, but I hope to not answer it interestingly.
Any more questions? Not, let's thank Josh again.